afternoon. I'm going to talk about organic materials. A lot of the properties that we are studying are not new in the sense that they are traditional material that has those kind of properties, but because of the ease of processing and the form factor that you could get from these organic materials, often we find applications that traditional materials cannot do. The way that we address those, the scientific issue we do is molecular engineering and processing control and structural properties relationship. What I'd like to do is to pick examples to illustrate all these 3 points. For the molecular engineering, we can design the molecular structures any way that you could draw a structure. But what we want to know is what kind of structures give us what kind of properties. So in this sense, we are more interested in knowing the design of the molecule rather than how to make the molecule, except at those cases where how you make the molecules make a big difference in the properties. Another area is processing control. A lot of times you may have the right chemical structures, but if you don't process it properly, you don't get the properties that you want. And the third area is structural properties relationship. We want to know how you change the chemistry, how you scale things up, how would that change the properties. And not only that, when you change one properties, how does that affect the other properties? The important point is that a lot of times for traditional materials, you have the primary properties that you want to use, but for applications, there are secondary properties that you need to use also. A lot of times you have to design around that. But for organic material, you could design the molecule so that it has the right set of properties for the right type of application. So for this portfolio, we cover many different applications. We are not application specific, but we use target applications to give us an idea of what kind of properties we should shoot for. So this portfolio is not focused on developing applications. We are focusing on getting material properties to enable new applications. The portfolio is organized around properties. So right now we have photonic materials, electronic materials. Any properties that's not related to these 2 areas, I lump them into novel properties. And also we address some of the issues in nanotechnology, but nanotechnology is really an approach that we use throughout all the property studies. And the investment strategy for this portfolio, how do we decide what properties to look at? We want to identify novel and unusual properties based on the latest research or the latest publications. Or sometimes it's by talking with the people in the laboratory, they identify properties that they do not have right now and are useful for certain applications. But then we decide, we want to determine whether there are scientific issues that's related to those properties. If it is something that we know how to do, but we just haven't done it yet, that's probably not these scientific issues. But if there are some knowledge that we are lacking in order to get the properties that we want, that's the scientific issue we want to address. And then we look at those properties, see how they are relevant to the Air Force applications. And also coordinate with other agencies to see if it's appropriate. And a lot of time, other agencies are looking at the same kind of properties too, but probably with a different type of materials, with a different type of chemistry. Then in each of the properties that we study, we try to promote complementary approach. want to have different ways to skin a cat, in other words. And we want to identify what are the critical issues. If there are gaps gaps that prevent this area to go forward, we will try to identify areas, projects to plug those gaps. And a lot of times, because we are studying a properties that probably will have many different applications, but we then focus the research effort on those properties target areas that are relevant to the Air Force. And we also leverage other TD's effort, especially those efforts not in the 6.1 area, because they are more focused on the applications. Their research let us define or refine the properties targeted that we want to research on. And we encourage international collaborations. A lot of time we find some unique capabilities from the overseas, but then we try to make sure there's a collaborating university in the US to have the collaboration. And we foster transition. A lot of time we take the PI to visit the lab, and sometimes take the scientists from the lab to visit the PI in order to have the cross-fertilization. And we use STTR a lot to do things that we cannot do under the 6.1 program. Because when you select 6.1 projects, you want to make sure there are scientific content, there are scientific values, but there are certain things that you need to do for the technology or for the science to go forward. So we try to do that under STTR. So I will go through each of the sub-areas and describe what we're interested in doing right now. For the photonic materials, we are interested in active material. That means the photonic properties of materials can be controlled to change. So we have nonlinear optical materials, Chi2 and Chi3. We also have photoreflective materials, and we also have advanced liquid crystals. And most of this, of course, because it is photonic materials, we focus on different types of photonic applications. But also, an important area that we cover is to counter laser applications. So for the Chi2 material, this is an area that we have been investigating for a long time for the electro-optic polymers. And we have made a lot of progress in this area. As a matter of fact, the materials right now, as a thin film, is 15 times better than lithium niobate. But when you put it into the device, because of the polling structures and so forth, we can only achieve 5x of lithium niobate. Even that would be a big improvement over the current technology. And right now, we use STTR in order to augment this area. One effort is trying to investigate the scale-up of the materials, because it's not just good enough to make the materials in the lab. If other engineers would like to use this material, they got to have available material. Therefore, this project is supposed to provide the material so other people can do the study. And also, we are working with the RX and RY to develop RF photonics. So we are making modulators that are suitable for that type of application. Another thing about the EO polymers, not only because of it is much bigger than lithium niobate in the EO coefficient, you could use it at places where lithium niobate cannot be used. Here is a structure that on a flexible substrate. You cannot do that with lithium niobate. And also because you make the structures based on photolithography, you could have a very complex photonic structures that would be difficult for lithium niobate. And here is a photonic crystal. We could fill this with electro-optic polymers so that we can have an active photonic crystal. And this is the latest work on silicon organic hybrid. Essentially, this is a silicon waveguide, and it has a very thin slot in between. We can fill that with electro-optic polymers and make the waveguide active. But we continue to address the fundamental. We want to make sure that in the device, it's not just 5x. We want to have the electro-optical efficient as high as possible. So what they are doing a combination of quantum mechanics and also molecular dynamics, doing a multi-scale modeling in order to understand the packing of the chromophore in the material. What we want to do is to translate the molecular properties, which is the nonlinearity of the chromophore, into materials that give us good nonlinear optical properties. What they have found is in a three-dimensional plot of dipole moment, chromophore concentration, and the EO coefficient, there was a peak at the intermediate dipole moment and low concentration area. This peak we have known since 2004, but the latest research found that there's another peak at high dipole moment and high concentration chromophore. Therefore, it gives you a very big EO coefficient. And right now, they were able to achieve in the device 15 times that of lithium niobate. As a matter of fact, there will be a publications coming out in Nature Photonics, where they're working with the engineers in Europe. They were able to demonstrate 100 gigabit modulation. And the efficiency is that for each bit is sub-femto joule per bit. That means for the modulator is sub-milliwatt for the modulator. And I was going to highlight this, but because the publication has not come out yet, and because it's collaboration with the European, so I didn't include that in here, but maybe next time I could talk about that. But even there, this type of study of the packing get a lot of attention in the scientific communities, because a lot of properties depends on how the molecules pack, not just the electro-optic polymers, magnetic properties, ferroelectric properties, all those depends on how the molecule packs, and even the protein folding depends on how the molecule packs. And then we also have the chi-free area. The chi-free area is changing of the photonic properties based on the intensity of the light. And we have been doing a lot of work in the imaginary component, the nonlinear absorption, that is primarily for laser protection applications. We want to vary the response of that and also have a large nonlinearity. But the real component is a change to the refractive index. It could be used for signal processing, it could be used for optical switching, optical computing. But what prevents us from doing that is that whenever you increase the real component, the imaginary component also increases. Therefore, you do not get the optimal switching that you want. And from theory, they said that you need the real component has to be larger than the imaginary component by a ratio of 12. So we developed a MURI topics, and it's started in 2009. And at that time, there's another proposal came in during the MURI solicitation that also have a complementary approach, but we can only fund one, so we funded the MURI at Georgia Tech and picked up the other one out of the core program at a much reduced level, maybe about one third of what the size of the MURI, in order to have a complementary approach. And in 2009, the figure of merit at that time, the real component over the imaginary component is 7. Right now, we can get 25, but that's only in solution. What we need to work on is how to get the 25 in a solid sample. Again, it goes back to how the molecules are packing. So that's why we are also interested in self-assembly of molecules at high concentration level as well as in the solid state. So if we could address that fundamental issues, it will have a lot of impact in many different areas. And I would like to talk about the photoreflective materials, because that's a good illustration of the secondary properties as well as the structure properties relationship. All this different type of applications came from the lab, from the Air Force lab. They are interested in all these different applications. They are all interested in photoreflectivities, but they all have different secondary requirements. For example, for laser protection from the Materials Directorate, what they want is the frequency response, the wavelength response, to cover as many areas as possible. Optical signal processing from the Sensor Directorate, what they want is a nonlinear transfer function between the input and the output. For the wavefront correction from the Direct Energy Directorate, what they are concerned about is the speed of the response, because they want to respond to the air turbulence disturbance of the wavefront. And then the Human Effectiveness Directorate like to use the material for 3D hologram display. For that, you cannot use a 1 centimeter sample, which all the other applications can do. What they want is a large area sample. Therefore, you need to change all the chemistry, do different type of processing in order to achieve that type of geometry. And then also image correlations. And this is very similar to the optical signal processing. So let me talk a little bit about this project on the target recognition. When we first started this project, we invited the Charles Wood, he's retired now, from Hanscom to come to our review. And he's already doing photoreflectivities with crystals. And then when the samples get to a certain point, when the materials develop to a certain degree of maturity, we ask them to take a look at the material. And they, because it's a new technology, there's different geometry and different setup are needed. So we took the PI and visited the lab in order to help do the transition. And then Jeff Corey started picking up the research, but he just left the Air Force. But anyway, they pick up a lab task in order to look at, for this type of application, what are the optimal material properties for organic materials, and also what are the secondary properties. First, they found out an important secondary property. They've been doing crystals, but they cannot do the correlation that they want because they cannot make the crystals sample thin enough. In order, because then you have an interface, therefore the reflected beam present another image that interfere with the image that you initially want. But for the organic material, we can make a micron thick film, therefore that's not an issue. Another issue is that for the scheme to work, they need to have a big difference between the two beams interfering in the sample. And you can see here, it's up to 25,000 difference between the two. So the reflectivity is important. Speed is not important here. That's why we sacrifice the speed in order to achieve the large reflectivities. And they use the synthetic aperture radar data, and this is the data with a lot of noise in it, and also other non-relevant targets, and this is the target, and they were able to pick out the target. And it is for the first time they claim that it's the first correlation filter that can improve simultaneously the signal-to-noise ratio, the peak-to-noise ratio, and also the discrimination. And it's because of material chemistry. I'm going to quickly skip over this part, but just talk about, mention that we're doing advanced liquid crystal for different type of applications. And liquid crystal can also be used for laser protection. And as a matter of fact, this is the work at Penn State. And right now, the nonlinear absorption that I talked about earlier are for short pulses, 10 to the minus 9 seconds and up. And for the filter, right now can do CW up to the 10 to the minus 6. But there's a gap in between. So what this group is doing is trying to look at existing mechanism, how to employ them for protection in this regime. And quickly, they found that there are two mechanisms they can exploit, and they also modify the material to improve the protection by 2 orders of magnitude. And they were able to model it in order to get a good framework to understand the mechanism, and also allow the application engineers, when they want to engineer the device, to use this mathematical formalism. And another area that we cover is electronic materials. We have programs in photovoltaics, and this is actually, the Navy also have investment in this area, so we have been having annual joint review in this area. My program goal is to get 10% efficiency out of polymer photovoltaics. We are achieving that already, so we are slowly backing out of that area. But the Navy is still continuing to invest in this area. As a matter of fact, they have a MURI in this area that's coming out. But we are focusing right now on understanding the radiation effect on organic photovoltaic for space application. Because of the lightweight and also the low cost, there are data that we can envision this could be useful for space short-term application, not for long-term like the existing satellite, maybe for a couple of years. So we are shifting to look at the space radiation effect. And we also have programs trying to find air-stable and conducting polymers. Right now, a lot of the polymers, conducting polymers, are P-type. You can make N-type, but they are not stable. It's because the HOMO is not low enough. So it's part of the research as to how to find good and stable conductors. And also, we want to improve the mobility of the semiconducting polymers. The semiconducting polymers are good enough to make transistors, but they are slow in speed, so it's good for certain type of application, like in display and things like that. People are using that. But if we can improve the mobility of those materials, then we could get into other regime of applications. But we are also looking at stretchable electronics. This is a new area that a lot of people are looking at right now. There are 2 traditional approaches right now, not traditional, 2 approaches people are using, because a lot of the electronics themselves, the active material especially, are not stretchable. So what people have been doing, one approach is to take a thin membrane of those active material, put them on a flexible substrate, and wrinkle them up. Therefore, when you stretch the substrate, those wrinkles will straighten out like an accordion, so that gives you a stretchable electronics. Another approach is to take the chip, which is not stretchable, and bond it into a flexible substrate, but have a flexible interconnect, so that when you stretch the substrate, the electronics still function. What we want is an active material that's stretchable. Organic conducting polymers are all below TG, below the glass transition temperature. In order for it to be intrinsically stretchable, you have to lower the glass transition temperature, and that's the scientific challenge. So there are different approaches. One is to how to modify the main chain of the polymers to make it below TG, above TG. And the other approach is to modify the side chain. But here's a third approach that is doing a blending. This is the work at UCLA. What they did is to blend the conducting polymers with a polymer, elastomer polymer, so to form a 2 continuous network. The conducting polymer is continuous, therefore they are still attached to the other 2 electrodes and still can function as electronic materials. But it's like a chicken wire. The wire itself is not stretchable, but the chicken wire is stretchable. And with the elastomer incorporated in there, they were able to stretch the light emitting device up to 130%. and still function, and it's repeatable. And they also have done field effect transistor, and also organic photovoltaic. And the interesting to note on the OPV is that when you stretch it, the efficiency goes down, but the power level goes up because you increase the surface area, and therefore you get more power out of it. Then I'll talk about the novel properties. There are many properties included in this area, but I'll just talk about three. One is magneto-optic polymers. The other one is flexible thermoelectric, and the omniphobic surfaces. So these are the three pictures that illustrate these three different areas. For magneto-optic polymers, it's measuring the Faraday effect. That is, you have a polarized light going through the material. Depending on the magnetic field that's present, it rotates by a certain amount. And this type of materials are used right now for optical isolators and different type of optical applications. But for polymers, when I visited Belgium at the University of Leuven, we start talking about this type of material. We found that it's 300 times better than the traditional material. So we funded them and also matched them up with University of Arizona in order to have a collaborative effort. But later on, we added on MIT. I'll explain why we had MIT later. The whole idea is to how to exploit the large Vedet constant that we can get from the organic material. But this property is very sensitive to the degree of regioregularity of the polymer chain. So that means for the regioregularity, that means this bond has to stay on this corner of the diaphragm along the polymer chain. If any one of them switch to this side, then you don't have the high degree of regioregularity that you want. To synthesize regioregular polymer, there's a lot of work being done in that area. But that is based, a lot of that is based on this McCulloch chemistry. And you make the material like this, so since this group can only react with this group, therefore when it polymerizes, they can, the R group is always pointing in the same direction. But there's a danger of this going through a halogen dance. That means these two groups can switch on you. Once it switches, then this group can react with this one with the R group pointing in the wrong direction. But because this is an R group, because of the steric hindrance, they cannot react. Only this one can polymerize, and therefore you have regioregular, high degree of regioregular polymers. But for this application, we cannot use the R group. We have to put an oxygen in there. This oxygen makes this monomer electron-rich, and therefore make it easier for this to do the halogen dance. You have to do a very low temperature reaction condition, but then it makes the polymerization difficult. Not only that, once it goes through the halogen dance, when they try to react, even though the oxygen and the oxygens are pointing in the same direction, but the R group can rotate out of the way. Therefore, they can react, and therefore destroy your regioregularity. So this is a work of Tim Swagger from MIT. Actually, this is the work, this project started with Ken Castor. He's interested in using living polymerization in order to do regioregular polymers. Living polymerization is not new, but a lot of the work that's been done are on aliphatic material. This is the first group to apply this type of chemistry to conjugated polymers. And you can see that So I asked him to see if he could apply this type of chemistry to oxydiolphine chemistry. And sure enough, and here's 3 samples. 2 of them are made with the old approach from Europe. And you can see that the properties varies very much. But with this approach, you consistently get the regioregular oxydiolphine. Therefore, the properties is much easier to study. So we're looking at the potential of using this for brainwave measurement. The current value with the modifications right now is about 1 order of magnitude away from measuring the brainwave. And we had a workshop with the TDs and also ONR, AIL, NSF participation. Right now, you could measure brainwave, the MRI, but it's very bulky, it's very expensive because you need to use superconducting material. But in the future, we could just use the fiber optics and you could do this type of measurement. And eventually, you could build it in all into a helmet, and therefore you could operators. The Army is also interested in it for diagnosis of MBTI, mild brain traumatic injuries. Another area is flexible thermoelectric. This is a publication in 2007. It's a theoretical paper. It says that the organic material could as high as a ZT, which is a figure of merit for thermoelectric material, as high as 25. Traditional materials is around 1. And then there's a science paper published at that time that were able to measure the thermoelectric properties of a single molecule. Therefore, we started a MURI to address this area, and also we started several single investigator programs in order to look at different approaches. So this is the work at Texas A&M with Chong-Ho Yu and Jamie Grumland. Essentially, what they are making is a carbon nanotube conductive polymers nanocomposite. The carbon nanotubes will transport both the phonon and the charge carrier. And the charge carrier can go through the conductive polymers to get to the next carbon nanotubes. But for the phonon, because of the mismatch between the vibrational energy of the polymers and the carbon nanotube gets scattered, therefore they transport the thermal energy, but keep the thermal transport down low. And this is the results that I shown last year. This is the traditional materials. They are getting within the same order of magnitude. But with the new work, which is not published yet, that's why I'm not showing it, they were able to use processing control to manipulate the charge carrier concentration. Right now, they were able to get the material properties up to several X of the traditional material. So we have a workshop also in this area with the different agencies and different TDs, and develop an STTR topics to address this area. Not only do we need to scale up this material for different applications, because all the traditional modules are based on bulk material. We have a thin film right now, so we need to know what is the proper module design to take advantage of the organic material. And we also have nanotechnology, and we address different type of chemistry. For example, people are growing carbon nanotubes. What we are focusing on is to grow a single type of chirality carbon nanotubes, because there's a lot of interesting properties you could get from the carbon nanotubes, but they have never translated into material properties. And I think part of the big reason is because when you grow them, you have a mixture of chirality. So we're interested in growing a single chirality. And also the graphene, right now you could grow large area in single layer or multi-layer, but it's not large quantity. What we want to do is use wet chemistry to scale up this synthesis, but retaining the electronic properties, and also the nanoparticle synthesis to make different, difficult to make particles. But I want to illustrate this part. This is a transition of 6.1 to 6.3 research. Initially, because this illustrates how, when you study properties, it can apply to different targets, and the targets kept evolving. This material came out from our MIRI studies in 2000, and they found that if you change this silica cages with the polymer outside group, fluorinated, it has very low surface energy. And so this is a collaboration between the propulsion directorate and the graduate student who graduated from MIT and went to Michigan. The original intent is to, when they develop a reusable launch vehicle, there's a shaft that connects the hydrocarbon chamber to the liquid oxygen chamber. And they don't want the hydrocarbon to go through, so they want to find the proper surface treatment. So not only applicable to this, RX, the materials directorate, as well as RV, they are interested in using this for phase transition material for thermal management. Because right now, most of that is using water. If they would like to go to other liquid besides water. So that shows you that interesting properties could have different applications. And then now they found that it could be useful for another applications. They can make any, based on this basic research, they can make any, not only oleophobic, they can make it any combination between oleophobic and hydrophilic and oleophilic and so forth. So this is what I illustrated 2 years ago. This is an oil-water emulsion. It's easy to separate oil and water, but an emulsion is very difficult to separate. They have two membranes in here. One membrane will only allow water to go through, but not oil. The other membrane will only allow water to go through, but not water. 2 minutes, so I can talk a little bit more. This is also solution processable. Therefore, you could dip coat any surface and get the properties that you want. So they could apply a wire gauze and coat all the wire to have these properties, but also leave gaps for the liquid to go through. You could do it with fabric to allow the liquid to go through, but give you the surface properties that you want. It would be difficult with some of the phobic surface approaches because they all use solid substrate in order to build a surface. So they were able to do this, and right now they have an effort in order to clean the fuel for overseas applications. You see the convoy going into Afghanistan, a large percentage of that convoy is for fuel. It's not because there's no fuel in Afghanistan. Their high sulfur fuel is good to run Russian equipment, but not US equipment. So essentially what they are doing is trying to change the plant size operation into a truck size scheme where you can transport it anywhere in the world and use a local fuel in order to run the US equipment. So that's just an illustration of the different application can evolve from doing one study. So in summary, the program is focused on getting new and interesting properties out of organic materials. And it's not application specific. It depends on what properties we're looking at. We try to identify the proper applications to use to do that. And we use those applications to help us identify the material properties that we want to focus on the research. So these are the areas that we are interested in, and this is how we do it. Thank you.
Okay, 19 seconds left, huh? Any questions? I just want to state that the effort that he was funding was a basic research effort on that system. He wasn't going out and saying, I want to make a truck-mounted fuel system to clean up fuel, because this is basic research. Yes?
Dr. Lee, you mentioned about some thermoelectric device with some glucose solution. I saw chart 24, I guess.
Chart 24.
Yeah. Oh, she moved on. Anyway, what is the efficiency? That's all my simple question.
What about that one?
24.
That is 24.
Next one? No, I don't see the chart I saw. Go back, please. This one, sorry, 23.
Okay.
Yeah, what is the efficiency of the thermoelectric device in?
The what?
Efficiency.
Oh, efficiency?
Yeah.
This is made out of old materials, so it's difficult to say what the efficiency is. I don't know the efficiency in terms of thermoelectric material, but they're talking about CT.
Conversion efficiency. Like fuels, I mean, solar cells, you have 24%, you have 15%, like that we say.
Well, it's embedded in the CT because it's, I don't know how to say the efficiency. I don't know that answer. Okay. But essentially, every measure of the effectiveness is by the CT. And most of the traditional materials is around 1, and now they are getting several factors larger than 1. And here, they were able to make wearable garment to power electronics, but it takes a long time right now because it's using the old material. We haven't tried the new material yet. Initially, we intended this to generate waste power from waste heat from the body, or use it to cool the individual pilots. But right now, we have identified many different applications, like making a cap and use that to power the night vision goggles so that you don't need to carry batteries, or use it on the handle of the medical equipment so that you don't need batteries, you just need to hold it. Or developing biosensors where you could use this type of material to power the biosensor.
All right, let's thank our speaker again. Okay, next up, Joycelyn Harrison.
We're here.